welcome Laura Alessandretti for this presentation. And she's from the university, the Technical University of Denmark, and she has been working on human dynamics and especially human mobility. And quite recently, she got a paper published in Nature about the scale of human mobility. So congratulations for that, and we hope to hear more about it now. And with no more delays, the floor is yours for your presentation. Thank you.
Yes. Hi, Mikael and everyone. Thank you very much for the introduction and also for the invitation. As I was saying, the lineup of speakers in the seminar series is amazing, and I'm honored to be part of them, of the invited speakers. And it's really a pleasure to meet you all and yeah, getting to know your lab and giving this presentation about my work. Now that I've tried screen sharing, I should make it work very smoothly and easily. So here we go. Here's my talk. So as Mikael said correctly, I'm going to explain my recent papers on the scales of human mobility that was published in Nature last November, but also other works on human mobility. So this is why I added the scales of human mobility and other mobility stories. Yes. So let's just get started. So I work on mobility. I try to understand how people move, and I do it for very good reasons, because it's really important to model well human mobility. So this has become very clear this year, when we've all seen papers on how human mobility models basically can help us do epidemics forecasting much better. Because viruses spread to people and people move, and we need to understand how we move to forecast the epidemics. But also human mobility has been studied forever, because we need to understand how people move in cities and how we can be better at forecasting traffic, for example, or at planning transportations and even planning urban spaces that are apt to fit our needs. So these are important reasons why people study mobility. And like the ultimate goal, especially from the application perspective, is to understand collective mobility flows. So here is a nice picture taken from a paper by Pappalardo et al. So this is not mine, where they model urban flows in Italy, and you can see like these beautiful maps of like moving human beings. And this is what we want to understand, like where people go, how do they get there? And we are interested in aggregated mobility, especially for applications. We're interested in how many people move. But my point is that to understand how these flows happen, we need to understand how single individuals take spatial decision. So my research is very much focused on the individual and how do single people take spatial decisions. And here I put a quote from Hagerstrand, who's one of the fathers of individual level human mobility, who says there are fundamental direct links between the micro situation of the individuals and large scale aggregated outcome. So here is like we really zoom into the individual, and we can because we have now amazing data for doing this. So I will start with the scales of human mobility, so which is my most recent work, and it was published in November, as we've seen. And this work was done with Sumin Lehmann and Ulf Aslak, who are two colleagues of mine from the DTU and KU University. And just to kind of like motivate you, the need for understanding human mobility in terms of spatial scales, I'd like to start with an example. Let's say that I was actually invited physically in Linköping. I would have to travel from Copenhagen for 357 kilometers, right? But let's imagine that instead the talk was going to be held in Norrköping, which is very close. And I don't know if I pronounced it correctly, but I guess you understand. The distance would be 389 kilometers. You know, from my perspective, it would make no difference at all. Like, I would really would not think about it twice. And probably even if it was in Stockholm or in Uppsala or anywhere else, or in Göteborg, anywhere else in Sweden, it wouldn't have made much of a difference for me to come over there. Why? Because it's sort of like the distance that I have to travel is at the level of like traveling between two countries, right? Actually, two neighboring countries, countries within Scandinavia. So like the distance that I have to travel is at the level of the country, and this is like all I care about. Instead, if one of you living in Linköping had to go to a supermarket in Norrköping, that would make much of a difference compared to going to a supermarket in Linköping, right? Like, because then you would have to go to a totally different city just for going to a supermarket. So the idea that when we think of traveling, we think in terms of spatial scales, we travel within our neighborhoods or within our city, it's really like intrinsic in the way we think of space. And actually, this is sort of well understood in the spatial cognition science, where it is clear that the way we think of space is in this like hierarchical fashion. The way we build these like cognitive maps of space are in a sort of hierarchical fashion. So we think of moving within a building, within a neighborhood, within a city, within the sort of like urban agglomeration, the region, the country, and so on. So this is really how we think of space and how our brain understands space. And in fact, in human geography, the concept of scale is really central to the literature on human mobility. So a key point in agreement among geographers and ecologists is that different processes operate at different scales and must be studied accordingly. So it is important to identify the operational scales of processes, and these are central challenges of research. And people really think about households, neighborhoods, cities, countries, and world, and the fact that different processes operate at different scales. Right, so this is clear. This is how we understand space and how theory think of spaces in terms of like nested hierarchical scales. Now, let's come to the literature on human mobility. So in recent years, there are many more studies on mobility. And because now we have digital traces that allows us to trace where people go and how they travel. So the literature on human mobility has flourished. And what have these studies found? Well, here I'm listing some of them that are published starting from 2006 until 2020. And many of these papers talk about scaling laws, scaling properties, scaling identities. So what this means is that this study did not find any scale in human mobility. These are all studies on human mobility, and all of them talk about this presence of these scaling laws, right? So there is some kind of like contradiction here with the theory and our intuition saying there exist scales, and then empirical studies did not find them. And I would like to go a little bit more into details of what it means. So when we study human mobility, what we do is that we take empirical traces that look more or less like what you're seeing appearing on the screen. And then we want to extract some properties from these traces. So what we extract is what we would call stops and moves, right? So from a trace, we extract the stops of every time a person stopped somewhere. And then we extract the displacements to another location. And we extract the length of the displacements and the duration of the stays. So these are important properties of a human trajectory. And what people have shown in these different studies is that when we plot the distribution of displacements and stays, we see power laws appearing. So we see this probability distribution that have no characteristic scale. So power law functions that appear like a straight line in a log-log scale, like we can see here, do not have typical scales. Why? Well, because even when we multiply the input by a constant, then basically the shape of the output is unchanged. So, so this is the reason why there's no characteristic scales in this like power law distributions, which characterize the distribution of displacements, length, and stays durations. Yes, and there's some level of controversy actually around whether power law distributions are the best to describe human mobility, but most studies until now agree on that. And importantly, due to this, all the state-of-the-art models for modeling individual level mobility assume that there are these scaling laws. So actually the state-of-the-art model is called the exploration and preferential return model, where a given agent located in a given place at a time t will wait at this place for a given time that is extracted from a power law distribution, and then will either explore a new place with a given probability, and in the case the agent explores, it will extract a distance from a power law distribution, or it will return to a previously visited place. And in this case, it will just use a preferential attachment. So this is like the state-of-the-art model in human mobility. And you can see that power law distributions are really embedded in this model. So like the question that we were asking ourselves a few years back is like, can we reconcile intuition, theory, and data? So I hope it is clear now that intuition says scale, theory says scale, and data says no scale. How come? Like our hypothesis was that scales are there, but are not so easy to see. And here I took an illustration from the New York Times from some years back, where basically I find it like so beautiful, and there's like so many scales together, so you can see like the streets. And if you're like located somewhere on top of a building in New York, you basically get to see like the micro scales with cars and people moving, and then like super far up to the ocean. And it seems like scales are so like nested together that somehow they're not easy to see. And in fact, this is also from like an analytical perspective, one can show that, say we have a given distribution with a characteristic scales, such as like a Gaussian distribution. Gaussian distribution is very well behaved, has a characteristic mean and standard deviation. Now, let's say we have 6 Gaussian distributions, and let's look at the mixture of these distributions. Let's look at like the joint probability of these distributions together. And now let's plot this in logarithmic scale, and let's keep adding more and more Gaussians. All of a sudden, we see a power law distribution appearing. So what is happening here is that by simply putting together distributions with different characteristic scales, and computing like the joint probability distributions, we end up having power law distributions appearing. And our hypothesis is that this could be also what happens with human mobility. We have so many scales. We travel within buildings, neighborhoods, cities, and regions that we don't see these scales. We only see power laws. Yes, so this distribution has a power law function in the tail. And we have even like shown, like we have some nice visualizations of like how this happens. These are interactive. You can explore them. So, okay, can we, if scales are there, but are just hard to see, can we find them? Like, how do we find scales starting from human trajectories? How do we extract them? We adopted a modeling perspective, and we tried to model space the same way that we think of space, right? So like in a hierarchical fashion. So let's imagine that each of us moves within a space that is characterized by this like hierarchical set of containers. So we have, in this schematic representation, we have location, black dots, encapsulated by buildings, blue containers, encapsulated by neighborhoods, orange containers, and you could like go further and further and have like really like a hierarchical set of containers. Let's imagine we move in this space, and let's imagine this structure shapes the way we move, so that whenever an individual is located somewhere, to decide where to go next, it will basically prefer sort of like a closer location that is in the same container instead of traveling to another container, so that there's a cost associated to travel to a different container. And this is like a generative model that we have also, we have an interactive visualization. Here it is observable notebooks, and I encourage you to explore. And the idea is that this model has like 3 characteristic elements. So the first element is the hierarchical partitioning of space. The second element is sort of like the attractiveness of each location. So some places are more attractive than others, or some containers are more attractive than others. And then the final element is the probability of transitioning at different scales. So it's basically much more likely, if I'm located in my room, to transition somewhere within my home rather than transitioning to a different container. So there's basically a cost associated to transitioning to containers that are located higher in the hierarchy. And then how do we move? Well, the probability of transitioning between location L and K is basically the product of two probabilities. So we choose first at which level we want to travel, and then we choose a location based on the attractiveness. So this is sort of like the core of the model. And this is like a generative model. So we can use this model to generate trajectories. So here what you can see is a trace that is generated by this container model. It's just like an agent-based model. And you can see that this trace looks incredibly realistic, or I've seen so many traces in my life that I think this looks realistic. And then when we look at the probability distribution of displacements, so the probability of traveling at a given distance, we can clearly color each transition based on how many containers one had to sort of, or how many levels in the hierarchy one had to travel across to get to destination. So some displacements, the blue ones, are sort of occurring at the lowest scale, and then other displacements occur at the highest scale, so the red ones. So you can think of like the red displacements are between countries, and the blue displacements are within your building, right? So we can color each displacement. And this is traces generated by the model. Now let's imagine that we didn't know the color. Let's imagine we only saw this trace generated by our model, and we didn't know at which scale at which level each transition occurred. Well, can we go back to the original hierarchy? So can we recover the original hierarchy? The answer is yes, because our model is clearly defined. So we can simply write the likelihood for a given displacement to occur, given a certain partitioning of the locations. So we have a trace, we have a candidate model, and we write the likelihood of each transition in the trace to occur given this potential hierarchical structure. So we write the likelihood of the trace given a candidate model, and then we can find the candidate model that is the most likely to have generated this trace by using maximum likelihood technique. So we can see that we can do this with the generated traces, so with the synthetic traces. And now, of course, once we have the system, it's very clear that we can do this also with real world traces. So this is what we did. We have a model for finding a hierarchical structure of containers, and let's just do it with real world data. So we took an incredible data set that collects the trajectories of 10 million individuals. This data set covers like few years, so it was collected starting from 2015 until today. It has global coverage, so individuals are located all over the world. It has super high temporal resolution, so yeah, we know exactly, like we have very high descriptions, very good descriptions of the trajectories, and also very high spatial resolution because it's GPS traces. And also some metadata, so like gender and age for each individual in the data. And we also have other data sets. So one is the Copenhagen network study data set that was collected in Copenhagen some years ago. And it's basically like an entire cohort of students that was given phones. And their mobility data was also collected. And then we also had some traces that were donated by volunteers. And what we did was we took some real traces. So here you can see a real trace, and we just applied the method that I just described to find the containers and the transitions levels. And we could basically color. So what we did is like via maximum likelihood to find like the best model that potentially originated this trajectory. So what you can see here on the left is the negative likelihood as a function of the container size. On the right-hand side, you have the location, and then we basically kept adding sort of like more and more levels to our description until we could not improve the likelihood anymore. And this basically resulted in us being able to color these trajectories and to assign like at which level each transition occurred. And this basically means that we can identify the containers for individuals. So here, this is an example for a user that approved to basically share the visualization with for presentations. And this person lives in Copenhagen. And here we can see these like blue containers correspond to the neighborhoods that this person would travel with. And these containers are called containers precisely because they contain this person's movement. And then we can find sort of at the following level, we can find cities that encapsulate neighborhoods. We can find regions that encapsulate cities. We can find macro regions that encapsulate regions, and so on, up to the scale of the continent. And basically we did this. So we found these polygons for there's like 1 million people in this dataset located all over the world. And what did we find? First of all, we found that people are characterized on average by like 4 hierarchical levels. Yes, so there's some level of variability across individuals, but sort of like the typical size is 4. And the second finding is that across individuals, when we look at the distribution of container sizes, we find that there are characteristic scales, so characteristic sizes for the containers. The first one corresponding to the neighborhood scale, so the neighborhood level that has approximately size 3 kilometers. And we have that there is an associated time scale associated to the typical spatial scale. So people tend to spend about half a day within the same neighborhood before transitioning. And then we have a second spatial scale, which is the city size, approximately 30 kilometers, and so on. We could find this like characteristic distribution across individuals. And as you can see, these are not broad distributions. These are log normal distributions. So they have characteristic sizes. There are characteristic scales in human mobility across individuals living all around the world. Why do we care about scale? Why is this important, this finding, this new modeling perspective for understanding mobility? The first reason is that we are much better at generating synthetic trajectories that look realistic and at predicting movements. So there's this like modeling idea that we have a new model that is better at predicting and at generating. So what we did to test this was for each individual to adopt a more like machine learning sort of perspective and train the model with a fraction or portion of the data for each individual, and then generating new movements. And basically we try to figure out how similar were the generated movements to the actual movements that this person took. So we compare the properties of the synthetic movements and unseen data. And we looked at different properties. So we looked at the distribution of displacements. And you can see here that the black line is the data. The orange line is our model. The blue line is the state-of-the-art model. You can see our model just like outperforms the existing individual level mobility model. We looked at the radius of gyration, which is basically measuring like the size of individual displacements. And again, our model outperforms the state-of-the-art. We looked at the distribution of location frequency, or like how long people spend in different places. And again, we outperform the state-of-the-art. And we looked at the entropy of locations. And again, we are much better at capturing the temporal correlations between displacements compared to the state-of-the-art. So putting all these results together, we really see that the model is just much better at generating synthetic movements. And also we compared with like a number of other models that also existed in the literature, finding that our model is outperforming the state-of-the-art. And the second key reason why we think this is extremely important is because it gives a new lens to understand mobility, and we show this. So some examples that I'm bringing up here, one is that we can basically understand differences across gender using this new model much better. So we looked at differences between males and females in our dataset. And what we found is that females tend to have smaller containers. So at all levels, they have smaller containers. This is known in the literature. The reason is that females typically travel less than men. However, they have a more complex hierarchical structure, meaning that they have more levels. So the mobility of women is somehow more complex, and this is captured by a nested hierarchical model with more levels. And importantly, we found that this difference between like the number of levels is not as pronounced in certain countries as it is in others. So you can see here in this figure, like in the left column, we have the distributions for a number of levels for females and males in the countries where the difference is the highest, which are Saudi Arabia, India, United Arab Emirates, and Turkey. And in the right column, you have the countries where the difference is the smallest, which are Norway, Denmark, Switzerland, and Ireland. And when we plot these differences in sort of like the structure of containers across for males and females against the gender inequality index, we saw like a strong correlation. So we showing that we could capture this like gender gap in human mobility that also reflects like the general inequality that there's in each country. And another important aspect we looked at is the urban-rural gap. So there's a lot of differences between individuals living in urban areas versus rural areas. And this is also captured by our model because rural users or people living in the countryside have a harder time accessing opportunities. So their containers are much larger compared to urban individuals. And when we looked at the distributions of container sizes for urban and rural individuals, we can see clear differences, especially at for lower levels. So at the level of the neighborhood and the city, urban individuals have much smaller containers. And to understand this even better, we looked at the effect of walkability. So walkability measures the characteristics of the physical environment that contribute to pedestrian-friendly neighborhoods. So areas like the one in the left-hand figure are highly walkable. You can see there's like lots of shops and people walking around. Areas such as the one in the right figure are less walkable because it's places where people need to drive, basically to get to shops and stuff. And in fact, we could see that the size of the containers correlate with the walkability. So in areas that are very walkable, where there's lots of opportunities, containers are smaller. In areas that are less walkable, containers are larger. So yeah, to sum up, we basically introduced like a new model that allowed to understand that human mobility is characterized by spatial scales. And we're now able to unveil these different spatial scales. And this new understanding of scales in human mobility allows us to better understand movements. And we have shown this by showing how this reflects in the gender gap in mobility, in differences between urban and rural users. But also this new model is able to generate synthetic trajectories that are much more realistic and we do not overfit. So basically, we can basically extrapolate movements even some months after we collected the data. This work is included in this paper. So there's much more in the paper than I've talked about. So I encourage you to read it if you're interested in the topic. That was published last November with Sune and Ulf. Yes, again, this was sort of like the topic of the talk, but I thought that because we have more time, I could also touch upon some other works that I've been working on. So I'm going to discuss a little bit about the exploitation trade-off in mobility. And I saw that last week you had Robin Dunbar, or some weeks back, you had Robin Dunbar as a speaker. So this is really to the point because the research I'm going to discuss, it's going to be really related to Dunbar's research on constraints in the size of the social circle for primates. And it's research that I've been conducting during my PhD that I did in London some years back, also with Sune Lehmann, but also with Andrea Baronchelli and Vedant Sekara and Piotr Sabiedziński. So the questions that we wanted to understand was like, how do we allocate time among locations, among different places? And if you think about it, so here is a map of London, and I was I like to show by starting like my own mobility when I was back there. So each pin here is basically a place where I've been at least once. And I was like, when I looked at the figure, I was like, okay, well, I've seen quite much of London, really. But then when I try to figure out like, where are the places where I spend 90% of my time? This boils down to a very small set of places. So the finding here was like, okay, I have visited many places, but really the places where I really go to a lot are very few. And they correspond to like a friend's place, my favorite bar, and my university, and of course my home location and so on. And this, of course, is like anecdotal, like my own life, but this is not just me, in fact. This is pretty much everyone. And this is something that has been found by many researchers studying mobility. Individuals are characterized by a small number of familiar locations. We call it the activity space. So the activity space of frequently visited locations, and it's really like a small fraction of the places that one would go to, but it's also the fraction of places where we spend most of our time. And there's different ways to operationalize the definition of activity space, but the key finding is really that there's a small set of places that we go and go again and again. And this makes human mobility highly predictable because we really like recurrently go to this set of few places. But at the same time, in the literature, there was another finding, which is that people keep exploring new places. So that people would keep going and going to new places. And here, what you see in this slide is basically the number of locations discovered over time in different data sets. And you can see that there's a trend, like a going trend, and it seems like even after a long time, it doesn't really saturate very quickly. So people keep exploring and exploring. And we were puzzled by this. We were like, how come there's this like exploration of new places always occurring, and at the same time there's only like a small subset of places that we always go to? What happens to this small subset of places as we keep exploring and figuring out, finding out new options for things to do? And our hypothesis was that these two different things were possible because no one had ever looked at what happens over long time scales. So this activity space of frequently visited locations sort of like is there because we're looking at snapshots of in time, right? So it's short time windows. Of course, if we look at like only a couple of months, then there's like a small subset of places we go to and this doesn't change. But what happens over years and years, like people must change these places that we like to go to. So we were like, we want to have like a longer term understanding of mobility and what happens to these activity spaces as we as time passes. And again, we took a lot of data and that was also like measuring mobility over long time scales, so years, and trying to understand what happens over long time scales. So we looked at two data sets again. One is the CNS data set that I mentioned before. It's collected at DTU, and it was mobile phones handed to students for some years. We look at the live log data, collecting mobility for 36,000 users over 20 months. And then we also use other data sets, so the reality mining and Lausanne mobile data collection data sets that are sort of standard and are some of the first experiments that were ever done for measuring like mobility and social interactions. So yes, using these two data sets, we were like interested in how these activity spaces of locations change over time. And when we look at long time scales, we find that actually activity spaces do change. So exploration induces a change in our life. Like we're not static. We are predictable, but to a certain extent, because things can change. So what you can see here is the similarity between this set of locations measured at any given time, and then like 100 days later, 200 days later, 300 days later, and so on. You can see the similarity decreasing. So when you go like 2 years after the first measurements, the activity space is only like 0.15 Jacquard similarity with the original activity space. So there are actually dramatic changes in the way we experience space over long time scales. And we were like, okay, but is there anything that doesn't change? And in fact, what we were surprised to find is that the number of places in this activity space, no matter how it is defined, doesn't really change. So there are, like at the level of the single individual, the number of places we go to doesn't change. And we thought this of like a sort of, we call it like spatial capacity. And it's basically the number of places that we would regularly go to and we would not forget. And And yeah, so we were kind of puzzled by this, and we were like, maybe it's just like due to the data that we're looking at. So we started with the CNS data, 850 individuals, and then we started looking at more data and adding more and more data points. We went up to 1,000 individuals, 1,100 individuals, 40,000 individuals, and still like this result would pop up that the number of places people would visit is constant over time, or this size of this activity space is constant over time, no matter how we define it. And when I say no matter how we define it is because, of course, there's like an operational definition of the activity space. And we figured that when we sort of like increase this window of time that we consider to count like what are the important places in our life, as we increase this window, then the number of important locations looks like it's saturated around like 25, 30 locations. So we have a spatial capacity of approximately like 25 locations. And another way to understand it or to think about this is that basically there is this like subset of locations that are important to each of us that has a finite size. And whenever a new location comes in, a previous location that we previously would go to is abandoned. So if we kind of like discover a new restaurant that we like to go to, there's a previous restaurant where we used to go to that it's abandoned, and we tend to keep only a small subset of favorite restaurant that has approximately the same size over time. Or this is like an anecdotal way to think about it. And another thing that is conserved, so it's not only the size or the number of places we go to, but also how we allocate time among locations. So we have basically looked at like places where we spend 48 hours to 168 hours per week. So this is just one actually, and it's the home location typically, or 24 to 48 hours per week. This could be like a work location, and so on, down to places where we spend like 10 to 30 minutes a week. And the way we allocate time among these different locations is also preserved in time. So there's no change in the number of places where we spend 10 minutes to 30 minutes per week. And yes, we were puzzled by like all these conservations in the way we experience space. So we wondered whether this is simply due to time constraints. So maybe we don't go to more places just because there's no more time for going to more places. So we ran some randomization experiments. So we took our data, we divided the data into chunks. So here is like a schematic representation. You can see that there's like 5 traces for 5 individuals. We divide them into days, and then we did some shuffling. So we shuffled traces within individuals, and then we even shuffled traces among individuals. And we were wondering like, what is different when we perform these randomization experiments? Well, we see that the capacity in the randomized traces is larger. So, so basically we could accommodate more places in our activity space, but we don't. So we could visit a restaurant that we used to like some years back, but we just don't. We have this like slow, sort of change in new places that we accommodate in our let's call it like a spatial memory, and we keep this small subset of places in the spatial memory, and sometimes we replace some, but the size is sort of fixed. And in the randomization experiment, we see that the Jacquard similarity does not evolve in time. So when we perform this randomization experiment, the activity space does not change. So this is really something intrinsic to behavior, that we slowly drift into like different life or spatial experiences over time. And so if you think about it, there's really something that has to do with memory. So we can encode this idea that there's a memory for a number of places that we can remember that are active in our memory. And another example that I like to give is think of recipes. So there's like, we know a lot of recipes that we like to cook at home, but then there's some that we used to do like a couple of years back. And whenever you're like, oh, what do I cook tonight? Like that thing that we used to cook like 2 years back, it never pop up in my mind. So there's only like a limited number of things that I remember I can think about. And this is sort of the same for restaurants. And so we encoded this idea of the spatial capacity and in a model. that is again the exploration and preferential return model I described before for individual mobility. And this model basically doesn't, in this model, individuals do not have a limited memory. So individuals explore with a given probability and return to places where they've been to before with the complementary probability. And then they can basically pick any place they've been to before. They can go back to a place they've been to years before. So we just like modified this model where agents are characterized by limited memory. And what we find when we add memory is that the model improves incredibly, because as you can see, like the blue line here is the Jacquard similarity of the activity space over time for the original model. When we include memory, we have the orange line, and this is basically showing like this slow drift that we also observe in real data. So introducing memory in the model basically allows for these observations, empirical observation, that the activity space is drifting in time. Yes, so this idea of the spatial capacity that is limited, and there's only like a small number of places that we regularly go to, reminded us of one finding from Dunbar's, or one of the very famous findings from his research, that individuals are characterized by a limited number of social contacts that they sort of like are familiar with, and that this number is bounded by cognitive limitations to about 150. And this somehow, like this finding in the spatial sciences reminded of this finding in the social sciences. And what we did was to look at a correlation between the social capacity, so the number of contacts that individuals keep over time, versus the spatial capacity. And we could do this because we have these data sets that are extremely rich, so not only capture human mobility, but also social interactions. So we could do it for the CNS data and for the NDC data that both collect trajectories and interactions. And we basically saw that there is like a positive correlation between the number of social interactions or social contacts that people that one would frequently contact or talk to, and the spatial capacity or number of places that people would go to. And we have verified that this is not due to data collection or anything. It's really intrinsic in behavior. So the more places, the more social contacts. And this is by no way like enough to say that the cognitive limitations that are responsible for these limits in the social capacity are also responsible for the limits in spatial capacity, but it's a hint that maybe there are some commonalities. So to conclude with this, our research ended like showing how do we balance the exploitation exploration trade-off. And what we found is that we allocate our time within an activity space of very few locations. And this activity space changes gradually over long time scales, but it has a constant size of about 25 locations, at least in the temporal duration that we have considered, which is a couple of years. And we also found that time allocation within this 25 locations is also persistent in time. And this fixed capacity is not a consequence of time constraints, so that there must be something else. And the model that includes memory as a possible sort of source of this limit is able to reproduce the empirical observations. So this work was also published a few years back in Nature Human Behavior with Piotr, Vedran, Sune, and Andrea, and it's evidence for a conserved quantity in human mobility. And again, there is a lot more in there than what I've been explaining here. So I encourage you to read it if you want to find out more. But also now we have some time for discussion, so probably I can address some of your doubts in this work. And that's it for me. I thank you very much for the attention, and I look forward to your questions. I can see that I'm a bit short actually, but I guess that's fine.
That's very good. Thank you very much, Laura. Maybe you could stop sharing your screen so that we can see the people, if it's okay for you.
Yeah.
And